Hi everyone, welcome to the second part of my Blender tutorial series, an introduction to geometry nodes. Today I'll introduce you to one of the most fundamental concepts behind geometry nodes. Fields. What are fields? According to Blender 4.2 manual, fundamentally a field is a function, a set of instructions that can transform an arbitrary number of inputs into a single output. So, you can think of it as a set of operations that we need to perform. Actually, we already did it in the first part of this series. This part of our geometry node system is a typical field. It's a really short one, but still a field. As I showed you before, the flow of what happens looks like this. First, we go here and take this geometry with us, and then we search for the spline factor attribute on every single point. Then, for every single point, we perform this operation, the equal node. So, for point 1 we perform this operation, and you can see the results are here in the spreadsheet editor. We haven't talked about this area of the geometry nodes tab before, but I think now is a good time to do that. The spreadsheet editor looks like a big table, somewhat like Excel. Its main purpose is to inspect attributes and field values. On the left side of the spreadsheet you can see all the different domains that you can switch between. We have basic measure type domains like vertex, edge, face, and face corners. What are face corners, you may ask? According to the Blender documentation, face corner domain attributes are associated with the corners of the face of the mesh. An example is a UV map attribute. To better understand the difference between face corners and other domains, let me show you these examples. As you can see, the vertex data specify a little bit more than just a face, even though they all consist of the same 4 vertices. It is similar to trying to select half of the face. We just get this gradient. Let's go to the second example to better show the difference. Here, we have 2 triangles with indices 0 and 1. We also have 6 vertices, 0, 1, 2, 3, 4 and 5, and 6 corner indices. I assigned different colors for different vertex indices and corner indices. As you can see, if we switch between domains, it looks the same. But let's join these 2 vertices together. Now, if you look at the vertex domain, we no longer have 2 different colors at vertex 0. But if we store our colors under face corner attributes, the 2 colors are still visible. This is because the face corner associates information not only with the vertex, but also with the corresponding face. So we now have only 1 vertex, but the face corner index is still the same. As you can see, indices 0 and 3 still represent the same corners. Great. Let's go back to our spreadsheet. The other remaining domains are curves, point cloud, volume grids, and instances. We can switch between them by just selecting the appropriate tab. Here we can see the number of elements for each domain type. For example, we have over 2000 vertices. Under the vertex tab you can see we have 2 attributes: position, which represents the position of each vertex in 3D space, and spline factor, the one we created before. As you can see, we can preview the value of the spline factor for each vertex. So, let's use our viewer node now. If we plug our attribute node into it, we can get 1 additional column in the spreadsheet labeled viewer. Currently, we are viewing the same attribute, so the values in these 2 columns are the same. Let's preview our equal node. Now we can see checkboxes indicating the results of every single comparison. Most of them are false, which is correct, as most of our donut is black in the viewport. To actually see if the spreadsheet is working, let's add an index node and plug it into the viewer node. Now, under the viewport overlays, enable attribute text, and let's choose 1 index, maybe index 0, the first one. Here it is in the spreadsheet. Now let's preview back the spline factor attribute, and as you can see, the value is 0, as in the viewport. So the equal value will be true, and it is. The spreadsheet area can be really useful for checking if your calculations are working as expected, and checking the values of attributes or fields, and few more things. Okay, enough theory for now. Let's start creating our first field using the Geometry Nodes editor and spreadsheet. Our main goal in this tutorial will be to create a displacement effect on our donut. For that, we will create a much complex field than this one, but don't worry, the process will be pretty straightforward. First of all, how can we change the position of our mesh to create a displacement effect? Before, we used the transform node for that. However, the transform node has one issue for our use case. It cannot use fields because the input are circular. What do I mean by that? As you can see, we have many different types of inputs. Colors represent different types of values like float, vector, boolean, and so on. But the shape indicates whenever it can use fields. Essentially, there are three types of shapes. A circular shape tells us that the input is a single value, like a single number. Circular inputs cannot accept fields because fields produce separate values for each element of the domain, like a vertex. As we saw before, we have different values of our spline factor attribute for each vertex. So our transform node cannot be used for displacement, only for offsetting geometry. The node that will allow us to do what we want is the set position node. Let's add it. As you can see, in this node we have all three different input shapes. We already talked about the circles. Let's talk about diamond shapes. The diamond shape indicates that the socket can accept a field as an input, so we can have different values for each vertex. It can also accept a single value if you want. The diamond with a dot inside the socket means that the socket can accept a field, but currently it is using a single value. Here we are using a single vector 0, 0, 0. Now that we know everything about sockets, let's try to use them. I want to create a large-scale noise displacement to add initial deformation to our donut. Let's plug in our set position node and think about how displacement works. We want to offset our geometry in its normal direction based on some sort of noise texture. If you don't know what the normal direction is, it's basically a direction that is perpendicular to the surface, like this. To get the normal direction, we can create a node named normal. As you can see, this is another node that doesn't have any input. It provides us with the normal direction, a vector for every single point. If you don't know what a vector is, it is a set of three numbers that represents the transformation or direction in 3D space. You can think of it as a little arrow that tells us how to move from point A to point B. Now, let's plug the normal into the offset input, and as you can see, our donut inflates a lot. This is because we are currently offsetting each point in its own normal direction. So the field is actually working. Every point has a different direction offset. To control the strength of this effect, we can add a vector math scale node. Let's add it and change the scale value. Perfect. This node essentially makes the vector shorter or longer. We need to have really small values, so I would add a simple multiply node, a basic math operation, to change numbers with greater precision. We can also add a value node, which is just a float number. Some nodes are hard to find because if you try to add a multiply node, for example, as you can see, we cannot find it. But if you drag and drop, we can. This is because this node isn't actually a multiply, but a math node. So if you want to find it, we need to search for math. Inside this node we can choose between many different math operations, not only multiply. Now that we know how to offset geometry in the normal direction, we just need to randomize the scale value based on some sort of noise. Let's create that noise with a noise texture node. To preview this noise, we can use a viewer node. Let's change the scale, and now we can create a second vector scale node and plug our noise into it. As you can see, now we have displacement. Perfect. Now, let's increase the contrast a little bit by using a color ramp node. You probably know this node from Blender shader editor, so let's add it and tweak the contrast. Perfect. Our displacement looks great. Our field is getting more complex, but it's pretty straightforward. First, we created a noise texture and increased the contrast. Then, we took the normal direction for each point. Now we scale this vector based on our noise texture. Finally, we make them shorter to control the intensity of the displacement. Now, I would like to have more randomization options for our noise texture. In the shader editor, we have something like a mapping node that allows us to move the noise. Here, we can do something similar but with different nodes. First, let's add a position node. This node outputs the position of each vertex, and this is how the noise texture is mapped by default. If we plug the position into the vector input of the noise texture, as you can see, nothing has changed. Now, let's add a vector math add node. As you can see, if we change the values of the second vector, we are moving our texture around. Great. If you look at the similar setup in the shader editor, we can see clear resemblance between the texture coordinate and position node and vector math and mapping node. We basically do the same thing but in geometry nodes. The last thing I would like to do to this offset is to make it more reusable. To do that, I will select these two nodes and group them using the Ctrl-G shortcut. Now, let's rename it to offset coordinate. It would be nice to have a slider to control the offset outside this group. To do that, let's go inside and create a new node, combine XYZ. This node creates a vector from 3 numbers. Let's plug it into the vector math node and the group input. To exit this group, you can press Tab or click this button. Perfect. Groups are a really nice way to organize your node tree. Furthermore, if we duplicate this group, you can see that now every change we make inside this group will affect all copies of this group, which can be really powerful. Let's plug this input value into our group input node. Change the type to integer and rename the label to seed. Now every time we change the seed value, we'll have a different offset. So this will be it for our first displacement. Now I would like to create a second one, but with a much smaller noise. To do this, I will need more geometry. Let's add subdivision surface node. This node needs no introduction. It's basically a subdivision surface modifier, but in the GeoNodes version. I think level 1 should be enough. Now, let's add a second displacement by duplicating this whole displacement setup. Let's plug it in after, and now we can change the noise scale and play with contrast and displacement strength. Perfect. So, we created our displacement. Great. The last thing I would like to show in this tutorial is remeshing. Remeshing is a process often used in sculpting that allows us to change the topology of geometry automatically recreating the original shape. We will use it here to create a little more organic results. It is really simple to remesh inside geometry nodes, we only need 2 nodes to do that. Let's add the mesh to volume and volume to mesh nodes. This setup will work basically as a voxel remesh modifier. Let's plug everything in and start adjusting the settings. In the first node we can set the voxel amount higher, maybe around 256. This will work basically as the resolution/voxel scale in the remesh process. The density parameter is responsible for the density of our volume. You can think of it as the density of a cloud. If it's too low, our mesh might shrink, but it will be smoother. If it is too high, our mesh will be the right size, but much more blocky. I think 11 is the right number for density in our case. The threshold value determines what is inside and what is outside the mesh. It's similar to density in the final effect. If we had more uneven clouds, it would control what part of the cloud is converted to the mesh. The adaptive value is some sort of dynamic resolution. If we start simply to bring the value up, our amount of geometry will be reduced and our shape will be simplified, but Blender will try its best to preserve all the details. So, this is basically all for remeshing. The last thing I would like to do is to make this a little bit smoother, because it is a bit blocky now. Normally, we would use a smooth modifier for this. Here, we need to recreate this with nodes, but don't worry, it is just 3 more nodes and only one is new. Let's add set position node and a position node. Plug the position into the position input. This time, as you can see, we are not using the offset input, but the position one. What we are doing now is assigning the same position that we already have for every point, so effectively nothing changes. To make this geometry smoother, we can add a blur attribute node between. If we increase the number of iterations, as you can see, we have a nice smoothing effect, which is exactly what we wanted. The blur attribute node will make the transition between different values in your attributes smoother. So it's perfect for making geometry smooth. We'll be using this setup quite often, so let's group it and plug the iteration into the input socket. Now let's rename it to smooth. And that will be it for this tutorial. So, we learned quite a few things and new techniques in this part. We created a powerful displacement field and recreated smooth modifier with fields too. Fields are a really powerful tool and one of the most important concepts in geometry nodes. You can try play with them on your own to better understand this concept. For example, you can try using different textures like Voronoi, or even mix multiple textures with mix color nodes. Have fun! Thank you so much for watching. I hope you learned something new in this tutorial. If you want to support my channel, you can check out the links in the description for my Blender add-ons and asset packs and the Blender file for the final donut on this tutorial. Thanks again for watching, see you again soon, and bye!